Hello again, my dear friends, and welcome to the last class in this series. In this last lesson, we're going to talk about notions of algorithms complexity. Well, we have talked about plenty of algorithms and techniques in this course. And now, to conclude, we would like to measure the complexity of these different techniques so that we decide on which technique to use or which algorithm to use. So in this presentation, we're going to talk about the measures of complexity and the algorithm analysis techniques, and there are apparently different ways of analyzing the different techniques. And we're going to look at some efficiency measures to do that. And then finally, we're going to talk about the big O notation, which we already have introduced actually a while ago, but we're going to talk about it a little bit more formally in this last presentation. Okay, let's start from measures of algorithm complexity. Well, basically, there is one very well-known measure that's called runtime complexity. And basically, it measures the amount of computer time the program or an algorithm needs to run to completion. Okay? So basically, I will count how many seconds, minutes, hours, milliseconds, microseconds that I need to run this piece of code on the machine. Another measure is the space complexity, and that has to do with the memory. So it measures basically the amount of memory that a program or an algorithm needs to run to completion. And for a perfect, ideal algorithm, I would like that algorithm to run as fast as possible with the minimum runtime and with the minimum usage of memory, of course. Can I always achieve this? I don't know, it depends, of course, and we're going to see the complications behind this. Running time of an algorithm. It's a critical resource, the CPU time basically, and it's a major concern. Why? Because this computer is serving so many applications at the same time. So the computer is not only mine, the CPU is not only mine, and it's not fully dedicated just to this application or to this algorithm. It's serving other applications as well. And that's why this time is very critical, and we have to utilize it in the best way possible. So among the factors affecting the running time of a program, the nature of the input to the program. Usually, the size is very important, is the most important. Actually, when I read data, when I input data to this program, the CPU is going to be waiting for the input machine to provide this data. And basically, the CPU is going to be sort of idle, just waiting for that slow device, the hard disk or the tape or whatever, to input that data. So this is a very critical factor. And as a matter of fact, that's one of the issues you should care about when you think about buying your computer. To buy a device that has a very fast runtime. Quality of the code generated. And that's your responsibility now as a professional programmer after you finish this Informatics 2 course. The quality of the code generated by the programmer and then by the compiler, of course. When you write your code, you're going to send it to the compiler so that it checks the syntax basically, and it will generate the object file. That object file will have basically all the basic operations, the low-level operations that need to be performed by the CPU, which resemble actually your program or your code. And then if the compiler generates the most efficient object file of your code, and if of course at the very beginning your code is written in the most efficient way, then you're going to have the least amount of time to run that code on the computer or on the CPU. Contention for resources with other users. As I said, you're not the only one. Your application is not the only application running on the computer. And all of these applications actually are competing together on using this, the CPU, or on using the RAM, the memory, or on using this resource or that resource. So basically, as we have lots of applications running on the same machine, that means all of these resources are basically looking at these resources, and they want to use these resources, and somehow we have to utilize these resources in the most efficient way to divide the time on their usage between these applications in the most efficient way possible. And of course, there are so many policies and there are so many techniques to do that, and it's beyond the scope of this course at this time at least. Nature and speed of the CPU. Well, do I have a slow machine, an old, let's say, processor, or a new one which runs faster at faster clock? The buses that I have, are they 32 bits wide, 64 bits wide, or even more than that, 128? Of course, whenever I have wider data paths and when I have larger sizes for the buses, definitely I can have more data through the system, back and forth between the system components, and then, of course, algorithms that we are going to run faster. Peripherals. And peripherals are basically the kind of interface devices that I have between the I/O devices like printers, keyboards, whatever, that are interfaced or connected to the computer. So if these kind of peripherals are state-of-the-art technology that run very fast and they can accept actually data at very high rates coming from the processor, and they can accumulate that data till the slow machine, the slow device like the printer absorb them, then definitely my computer, the requests at least coming from the user or my application are going to run faster. So basically, this has to do with the computer system that you have. Time complexity of the algorithm underlying the program. What is exactly the algorithm that you are using? Okay, and as we said, we have covered different algorithms for sorting, for example, or for searching. So the complexity of the algorithm has to do with the how many computations I need to perform to get through with the task. So basically all searching techniques lead to the same thing, to return to your target. Well, but of course, these different techniques needs different number of comparisons, assignments, changes, checks, and so forth. So the complexity, the amount of time this application needs on the computer depends upon the complexity of the implemented algorithm in your application. How to measure the time complexity? Well, we could do some sort of empirical comparison. And that's by just experimenting with different data patterns using the different algorithms, all right, that we have in hand. And then I will decide, I will see, put marker when I start, marker when I stop, and I will check which one of the algorithms gives me the best result. Well, can I generalize my results in here? Well, it depends upon the nature of the data you're experimenting with. Of course, to generalize statistically your results, then you have to have a huge number of data sets that you experiment with before you can generalize this. And not only number of data samples that you have, but rather the quality of this data. Does it represent all possible scenarios, all possible cases? Typically, we have some sort of benchmark test data, and this kind of data is used actually to compare between the different algorithms. Or another way of doing that is the asymptotic algorithm analysis, an estimating technique basically. How does that work? We're going to see actually. Yes, we're going to do some sort of a time analysis kind of thing. To compare this algorithm with that algorithm to see which one takes more time, basically more time on the CPU than the other. The algorithm analysis technique. Well, we don't actually measure the running time. Why? Well, I don't know what's the underlying machine I'm running this program on. So I cannot write my code here on my computer, on this computer, and claim that, well, my technique only requires 3 seconds to perform the task. Okay? Try your algorithm now on your machine and tell me how much time. Oh, you take 5 seconds, so mine is better. Well, I don't know, maybe this computer is different from the computer you're working on. Right? Your computer could be, just because its CPU is slower or its memory size is less than what I have in here, that's why you needed the 5 seconds. All right? However, if you come here and run your algorithm in here, you could need something like 2.5 seconds. And that way, your algorithm is better than mine. So we have to compare always apples to apples. So instead of looking at the running time, Okay, we're going to be instead looking at the number of comparisons, number of assignments, number of operations performed. Okay, so the actual time could vary greatly from one CPU to the other. It varies depending on the memory size from here to there, and many other factors as we mentioned earlier. So we estimate running time by counting the number of basic operations that are required to process an input to get of a certain size to get the output. The number of basic operations rather than the actual time in seconds. Basic operations is the dominant operation actually performed by the algorithm to be accomplished. We don't care about these little operations here and there that occur only once in the process. Okay, like when you print to the screen or when you scan input from the keyboard or something like that. These are not major operations. Basic operations, we mean by that, as we of course already analyzed lots of algorithms, the number of assignments that I do a lot, or the number of comparisons that I perform a lot in my program. That's what's dominant, and that's what I care about, because these are the major operations that I do throughout the program or throughout the algorithm I'm developing. So to compare this algorithm with that, I will be looking at the basic number, the number of basic operations rather than the actual time it takes to perform these operations on this machine or that machine. This is a more realistic measure rather than the execution time. So its time to execute does not depend on the value of its operands. All right? It only depends upon the number of operations. Running time is expressed as a function of n, where n is the size of the input, and f is some sort of a function defined on the number of inputs. Okay? So basically, if I have a list of size 1,000, then the running time is going to be approximately some sort of a function based on n. So basically, as n grows, the value of this function is going to grow accordingly. So the function f of n actually expresses a growth rate, the rate at which the cost, or the cost in this case is the runtime of an algorithm, grows as the size of the input grows. Okay? And we look at what we call, again, the growth rate or the behavior of the algorithm in terms of the number of computations. That's a very close, actually, approximation to the runtime rather than measuring seconds again. Let's look at an illustrative example. Let's consider having three different functions, three different algorithms, basically, that are going to accomplish the same task. The task is to square a number. Given number n, I would like to get n squared. Okay? How can I do that? Well, let's look at the three sample algorithms that could perform that. Well, sample one, basically, I'm going to make an assignment to where sum equals to n squared. Of course, my computer has to have this engine that multiplies a number by itself, a number by a number, multiplier. Sample two, well, another way of doing n squared is to make a loop like this, initialize your sum to 0, and then go from I equals 1 to n, and then say each time sum equals sum plus n. So you're adding n to itself n times, right? Adding n to itself n times, that means it's n times n. That's another way of doing it. So it works. The third example is to where I'm going to initialize again my accumulator with 0, but this time I'm going to have two loops. Okay? Each one of them going from 1 to n, 1 to n. So this inner loop is going to go n times, and this outer loop is going to go n times as well. Each time, the accumulator is going to be incremented by 1. All right? So with each major loop, I'm going to be adding n times. And then with the outer loop running n times, that means I'm going to have n times n. So basically, again, sum will equal, once I exit these two loops, sum is going to contain n squared. So basically, all these algorithms perform the same task, squaring the number. However, if I look now into the complexity of these three algorithms, we're going to find that their performance is going to be different. Let's look at the assumptions here. The assumptions I'm making is that basic operations are basically assignments, is all what I'm doing. And that's what's going to take the major time. That's why all other small assignments here and there are going to be ignored, like the time for the loop to increment its index and go to the next. This is not a major thing, okay? So the assignment, okay, is the major step or the major basic operation, dominant basic operation I'm performing. Other operations, I'm going to assume that they take no time, no big deal. So measurement of runtime for this. For these three scenarios. Measurement of runtime is performed by counting number of basic operations, basically assignments in this example that I make, whether I'm talking about sample 1, 2, or 3. And I'm going to take this number of operations as a measure of the runtime for this particular algorithm or that. Okay, based on this, let's look at sample 1. Sample 1 always does the same amount of work regardless of what is in, right? It performs only actually one assignment. It multiplies n by itself and put it in sum and it returns, right? So whether n equals to 5, I'm going to make one assignment. If n equals to 50, it's again 50 times 50, one assignment. If it's 500, 5,000, it's the same, one assignment. So one basic operation is performed and the whole task is done, regardless of the input in. So in this case, the number of assignments and then the runtime is kind of constant, regardless of n. Okay, let's look at sample 2. Well, in sample 2, I iterate from 1 to n, and each time I accumulate in my accumulator sum by adding n to it each time. Well, that means I'm going to go from 1 to n. Well, this loop is going to iterate again and again based on n, making one assignment each time it iterates. Well, in that case, if n equals to 5, then I have one assignment outside, and that's when I initialize my sum to be 0. Okay, and then the loop is going to iterate 5 times. Each time I'm making one assignment, so I have 5 assignments inside the loop, 1 outside, so a total of 6. If n equals 50, the loop is going to iterate 50 times, and that means I'm going to have 51 assignments. If n goes to 500, then I'm going to have 501 assignments. So basically, as the number n grows, all right, the number of assignments that I make grow at the same rate. So it's like a linear, if you like, behavior. And that's the growth rate function. It was constant in sample 1, and now it grows linearly. Sample 3. Well, this one grows. I have 2 loops, remember, to calculate this. So it grows with n squared, as a matter of fact. Because it's for n equals, let's say, to 5, I will have one assignment outside, and then 5 times 5, 2 loops inside. Each one of them goes from 1 to 5, okay? And the inner loop iterates n times each time the outer loop iterates once. So that's like 5 times 5, 25 plus 1 outside, that's 26. Right? If I have an n of 50, then I'm going to have 50 times 50, and that's like 2500 plus 1 outside. If it is 500, then it grows to this big number. So the behavior of growth actually is going very fast in the order of n squared. Right? So yes, the 3 algorithms are basically doing the same thing. However, with each algorithm having a different number of computations, and that means the runtime for this algorithm or that algorithm is going to be different. All right? And that's how then we measure the performance of this technique or that technique, by looking at the runtime. So what is the runtime of each of the algorithms shown above? Well, assume that the amount of time required to make an assignment is the same constant c, some magic number. All right? Let's say 5 seconds to make an assignment. I'm exaggerating with my numbers in here. Then the runtimes for the algorithm above are as follows. For the first sample code, remember, the number of assignments was just once. So that once requires c seconds. So basically, my function f of n equals to c, and it's always constant regardless of this n. Right? One assignment only, and that assignment takes this much of time. However, for the second function, I will perform n plus 1 assignments, and each one of them takes c seconds. And that means I'm having like c times n plus c seconds. All right? Much bigger than this. It grows as n grows linearly. This is a linear operation. Sample 3. Well, remember that we have n squared plus 1 assignments, right? And if each one of them takes c seconds, then the total will be c times n squared plus c. So the behavior in here is a quadratic. All right? So to look at this in a sort of graphical view, then basically the first one had a constant behavior c, and this is called a constant growth rate. And it's represented by this blue line in here. It's constant regardless of n. Always the time I need, which is represented by this f of n, is basically constant, equals to c. However, for the case of the second sample function, or the second algorithm, it was something like c times n plus c. So basically, I'm having a sort of a linear growth rate, c times n. This is the dominant factor. Okay? So it increases linearly as n increases. Okay? And at some point, all right, this value is gonna be much more than doing the task using this sample function. Looking at the third behavior function, which was quadratic, c times n squared, it's a parabola like this. And it grows even much faster than this when I have a large n. So as n grows, then this one and this one, they vary. However, for the first one, it was constant throughout. Again, the growth rate of this and this are again different, and I have a faster growth rate for the quadratic rate that's represented in the third sample function as compared to the linear growth rate we have in here. Okay, so that's basically the idea behind analyzing the runtime and actually the number of computations making the dominant part of the algorithm when we do this or do that. In real practice, there are so many common growth rates, as a matter of fact, that the algorithms follow. And of course, it depends upon the algorithm complexity. Basically, some algorithms have constant growth rate. And that means regardless of the size of the input, they always perform the same. And they always have some constant number of operations and so forth, constant execution time. All right? However, some others use the linear, which we looked at. Some functions and some algorithms, and we have seen some of these, actually behave at the order of log to the base n. And this is a logarithmic kind of scale rather than a linear scale. All right? And then the growth rate in here is slower than this one. All right? And some others perform like n times log n. And it's basically called n log n. And we remember seeing this when we were talking about the merge sort, if you all remember that. Some others are quadratic, like the one we saw in the second sample function we were talking about in here. Or cubic, this is even worse. Or 2 to the power n, exponential, and this grows very fast, okay? So the slower that rate is, whether this function or that, the slower the rate is, the better that this algorithm performs when it runs on a machine. Okay? We don't like the high rates because that means they will need more and more operations as the size of the input increases. And this is, of course, a problem because it's going to take more time on the CPU. And of course, in that case, the CPU is going to be dedicated to this algorithm and it's preventing other applications from using it. So the lower the rate of growth, the more attractive the algorithm is. Efficiency measures. Well, efficiency measures are basically calculated in terms what is the best case, and that's when you're luckiest, or maybe the worst case, or sometimes people like to look at the average cases. All right? And which one do we look at? Actually, we look at all of them usually, and it depends upon the application. Sometimes you're going to be looking at the worst case because it's critical, timing critical, and sometimes you look at just the best case. Normally people look at the average case, so it depends upon the application in hand. Example, consider the sequential search. In sequential search, if you all remember, if I want to search a list of size n looking for the value k, then it depends upon where that k is located actually in the list. The question is, how many list elements I need to check before I can find my target k in the list? Well, in sequential search, if I would like to talk about the best, then the best, if I find k as the first entry in there. So in that case, just one comparison and I'm lucky. So that's the best case. Do I look always at the best case? I don't think it's very much informative about the technique. Well, how about the average? Well, on average, we did the analysis. On average, if I have n entries, then I will go halfway and hopefully I'm gonna find it. And we have done the analysis before, right? So actually, on the average, I'm gonna do n over 2 comparisons till I find my target k. Well, if k is the last element in the list, then that's the worst scenario possible. And that's the worst case, basically. And in that case, I need to perform comparisons with all entries till I get to my target. And that means I'm going to be performing n comparisons. So 1 for best, n for worst, and in this case, n over 2 as an average. The most useful analysis are the average and worst cases analysis. The best is not very informative about the technique, actually. This is the beginner's luck, they call it. So I don't rely much on that one. Average case analysis, compute the cost of a search for all possible elements and then take an average of them. And we have done this for the case of the sequential search. We're repeating that very quickly in here. If it's in the first position, I need 1 comparison. Second position, 2 comparisons. Nth position, n comparisons. So these are all the scenarios, okay? So the average is basically to sum them all together and divide by their number. Well, here's the sum, okay? It's something like this. And this comes to something like n plus 1 divided by 2, okay? And we have seen this equation before. It's n over 2 or n plus 1 over 2, the same thing. Asymptotic analysis. That's the second way of looking at things. Ignore constants for large values of n. Like 10n and 5n, they don't significantly different, especially when n is very large. So these details are not really very important, especially when n is very large. So the behavior of this cost function and this cost function are practically the same. So basically, n plus 5 or n or even n plus 50, they more or less mean the same. of course, that's when I have very large n. Otherwise, of course, the thing is critical and I cannot use asymptotic analysis. N plus 5, n plus 50, 10n, 5n, 5n plus 10. Basically, they don't differ that much. Okay? I can always say that in the same order, more or less, especially when n is very large. So in this case, I look at the what's so-called big O notation, the order of computations rather than the exact number of computations. And we have, of course, talked about this. We have seen this big O notation before. It is part of this asymptotic analysis of the algorithms. Okay? The big O notation is used to express an expression in an approximate form that denotes the dominant term, the major term in the expression. So based on that, 10n and 5n, basically, they're in the order of n. So I can express them as O, big O, n. And they mean basically the same, especially when n is large again. These three expressions, again, can be expressed as order of n because the dominant factor is n in all of them. Well, these terms altogether are, again, the dominant factor is n. Yes, I'm multiplying with 5 with 10, but if this is million, talking about a million entry or 10 million entry, more or less, means the same, almost the same growth rate. And that's why I express all of them in this big O notation as order of n. Well, if my function is something like this, 5n squared plus 3n minus 4, then in the big O notation, I can write it based on the most significant term, which is n squared in here, as order of n squared. This example in here, I have 1,000 times n plus 28. This 1,000 is actually very big, but it's still constant, right? So the most significant term in here again is n. So again, if I want to write this in the big O notation, I say order of n, even if this number is very large. I'm looking at the variable that I have in here, which is n, and I'm looking basically at the dominant factor containing n. And again, I can express this as order of n. Term used to describe running times. Well, we use basically upper bounds. And that means the ceiling, if you wish, of the number of computations. The highest growth rate that a function can have. So sometimes refers to as big O notation kind of thing. And we denote it by order of the behavior function or the growth rate function, order of f of n. Remember this f of n, it's the cost function that we use to express the runtime. And instead of writing the exact function, we just express it in terms of the big O notation again. So as a definition, if f of n is in the set of order of g of n, if this function is in the same order as this one, if there exist two positive constants, c and n naught, such that the absolute value of f of n is less than the absolute value of g of n times c for all n greater than this breaking critical point. Okay? And that means that these two functions are in the same order within constant c after certain breaking point n. So n0 is the smallest value for n for which I can consider this to be like an upper bound on the function f of n. The usage, the algorithm basically is in the order of n squared in best, average, or worst case, means for all data sets big enough, that means n is greater than certain breaking point in 0, the algorithm always executes in less than c times the g of n, this cost function, steps in the best, average, or worst case. It depends upon which actually one we're analyzing. Examples. Let's say the cost function is like 3n plus 4. Well, I can express this as in the order of n. So my g of n is n actually. And this is just c times this one, right? And that's why I can put this as order of n. So I can just say f of n is in the order of n as the dominant factor in here. Because basically 3n plus 5 or plus 4 is always less than for n, but for all n greater than 5. So my n0 here is 5. So C0, C, the multiplying constant is 4, and the n0 is this critical point 5. So then, for values of n less than 5, for n is not an upper bound, but rather it is going to be an upper bound for n greater than 5. And in that case, I can say that it's in the order of 4n. Another example. F of n equals to 10n squared plus 4n plus 2. Well, this is in the order of n squared, right? Because this is the dominant factor that I have. Well, I know for sure that n squared, this function, plus 4n, 10n squared plus 4n plus 2 is always less than 11n squared for n greater than 4. That's for sure, and we can prove that. You can do it yourself. Well, if that is the case, then I can say that this function is in the order of 11n squared for n greater than 4. Important remark. Note, the function of example 1, which we have seen, is also in the order of n squared. Well, how that comes? The dominant factor in there was n, right? I didn't have n squared. Well, why would it be then in the order of n squared? Well, since 3n, that's the function that I have, is always less than n squared, right? So this is like a ceiling. This is like an upper bound for all n greater than 3. So if that is the case, then I can say that for n greater than 3, this is the ceiling. So the behavior of this is in the order of n squared. Is that true? Yes, it's true. This is a fact. Okay, so this is the upper bound, and well, according to the definition we just introduced a few slides ago, then I can always say that my function is in the order of whatever bound you have. However, in order for the big O notation to be meaningful, all right, I then have to be very strict about this upper bound. What am I trying to say in here? Well, this height is definitely higher than this. So I can say that the tables that I have are always lower than this ceiling. This is true. However, it's true as well to say something like, well, all my tables, if you can see my hand on the TV screen anyway, okay, my tables are always lower than this. This is a bound. This is true. However, this is not very meaningful, right? This is more meaningful, more realistic. The tables that I have are always less than this bound. So I have to have the bound always closer to the actual expression that I have. So to be more meaningful, we need to the tightest, the closest, the smallest upper bound closer to the actual expression. And in this sense, I cannot say that the 4n plus 3 is in the order of n squared. All right? So thus, it's not accurate to say that 3n plus 4 is in the order of n squared. It's not meaningful. Yes, n squared is always larger than this, but it's way larger. I'm not going to refer to it as my upper bound to go to that. Sum and product rules. Well, given two program segments, program 1 and program 2, such that B1 is in the order of f of n and B2 is in the order of g of n. All right? what is the runtime complexity now of an algorithm which is going to combine these two? All right. Well, how am I going to execute these two? The question is, if execution of P1 follows the execution of the execution of P2 follows the execution of P1. So that means I'm going to execute the first one, which is going to take in the order of f of n. And then after that, f2, all right, or B2, which is basically going to take the order of g of n computations. How much time do I need to execute both? Well, I think it's since we're talking about the order, something like this. First segment followed by the second segment. Well, the order of the complexity is the worst of the two, right? It's the max of the order of the first and the second, basically, whichever greater. That is, the segment that takes the most time dominates, basically. Well, what if the second segment executes inside the first segment? Well, this is like multiplication, because I'm going to repeat this inner one many times as this one goes, actually. Well, in that case, then the complexity will be something like this. The order of g of n times f of n, because I'm repeating this time that many times. And that means the product of the two functions rather than the max or the sum or anything else. Okay, that's it. This is the last slide of the last lesson in this course. Hope you enjoyed it. To refer to this material, you can go to the internet, to the UNINETTUNO website, click on the UNINETTUNO project, and you're going to find lots of interesting stuff as usual. Bye-bye.